satellite is only as good as its connection to Earth. But for small satellites, every gram counts. Every millimeter is precious. So what if you didn't have to add an antenna? What if the satellite's very body became the antenna? This isn't science fiction. It's the reality of additive manufacturing, and it's completely changing how we build our windows to the universe: small satellite antennas. For decades, satellite design has faced a fundamental trade-off. To launch something into orbit, it needs to be as light and compact as possible. Every kilogram can cost thousands of dollars. But high-performance antennas, the kind needed for fast data transfer, are often bulky, heavy, and have fixed, awkward shapes that are difficult to stow. This creates a constant battle between form and function. Engineers have to compromise on antenna performance just to make it fit inside the satellite's tiny frame. Enter additive manufacturing, more commonly known as 3D printing. Instead of carving away from a block of material, it builds objects layer by microscopic layer. This process unlocks a new dimension of design freedom. Antennas are no longer limited by what a machine can cut, but only by the laws of physics and an engineer's imagination. We're not just printing with plastic. Advanced techniques allow for printing with metals like aluminum and titanium, or even specialized conductive polymers. These materials can be combined in a single print, creating integrated structures with both dielectric and conductive properties, which is the very essence of an antenna. This leads to the first major breakthrough: conformal antennas. Instead of a separate component, the antenna can be printed directly onto the structural panels of the satellite. The satellite's own skin becomes the antenna, saving an immense amount of internal volume and completely eliminating bulky deployment mechanisms. The second benefit is radical optimization. Engineers can design and print complex geometries, like helical or fractal antennas, that are perfectly tuned for specific frequencies. These intricate shapes, nearly impossible to make traditionally, can dramatically increase an antenna's gain and efficiency without increasing its size. And third, there's speed and cost. Rapid prototyping means new designs can be printed and tested in days, not months, drastically accelerating innovation. So what does this mean for the future of space? For Earth observation satellites, it means higher bandwidth to send back massive, high-resolution images and climate data. For satellite internet constellations, it means smaller, cheaper, more capable satellites that can be mass-produced and deployed faster than ever before. We can even print multi-band antennas, where a single structure can communicate across different frequency bands, reducing the total number of components. This consolidation is key. We can integrate waveguides, filters, and feed horns directly into the antenna structure, creating a single, lightweight RF front end. The weight savings are staggering. In some cases, a 3D printed antenna can be over 50% lighter than its traditionally manufactured counterpart. Lower mass directly equals lower launch costs, making space more accessible for universities, startups, and developing nations. The technology is also pushing the boundaries of deep space communication. Imagine antennas for missions to Mars or Jupiter, optimized for transmitting weak signals across vast distances. Of course, challenges remain. We need to ensure these printed materials can survive the brutal environment of space: extreme temperatures, vacuum, and constant radiation. Rigorous testing is underway, subjecting these components to thermal vacuum chambers and vibration tables to simulate the violence of a rocket launch and the harshness of orbit. Material science is another frontier. Researchers are developing new printable alloys and polymers with even better RF performance and space-rated durability. The ultimate goal? Multifunctional structures. Imagine a satellite panel that is simultaneously a load-bearing element, a radiator to shed heat, and a high-gain antenna. The next step might even be manufacturing in space itself. Satellites could print and deploy specialized antennas in orbit, custom-built for the mission at hand. From saving wheat and money to enabling entirely new designs and mission concepts, 3D printed antennas are a quiet but profound revolution. They are making our smallest satellites more powerful and our connection to the cosmos stronger, more reliable, and more accessible than ever before. The next great leap in space communication isn't just being launched, it's being printed, one layer at a time.